It's a pleasure to introduce Nikolay Grantcharov, our very own organizer of the BunG seminar, and he will be speaking on the local and global Hitchin vibrator, or Hitchin map.
Thank you for the introduction. So yes, I will discuss the local and global Hitchin map, with the ultimate goal being to prove that the Hitchin map produces the family of Poisson commuting functions on the cotangent bundle of BunG. So there will be sort of 3 parts in this talk. In the first part, we're going to discuss Hamiltonian reduction in the classical sense. Okay, so let K be an algebraic group over the complex numbers, and suppose that it acts on a smooth scheme Y. Also over C, and consider the quotient stack. To be Y mod K, so I mod out the left K action. So I'm also going to make this assumption that this quotient stack is good. So this is the assumption that we will be using, and I'll highlight where we use it. In the case of an algebraic group, so it's like something of finite type, then this quotient is automatically good. But we're going to want to consider cases like K is G of O, the form of this, and in that case, we'll need some minor assumptions additional to smooth scale. And to remind you, good means that the dimension of the cotangent bundle is equal to twice the dimension of the set. So usually it's at least twice, but when it's good, it's exactly twice. And what Hamiltonian reduction does is it allows you to compute the cotangent bundle of this quotient stack. So there's a moment map. So differentiates the K action on Y to induce the so-called co-moment map. So this is a linear map from the Lie algebra of K to the vector fields on Y. And then if you take the dual, this is called the moment map. This is mapping the cotangent bundle of Y to the dual of the Lie algebra. We call this the moment. And then the main result of reduction states that the cotangent stack of this quotient stack is equal to the fiber over 0 of the moment map modulo the K action. And this is an equality of stacks. And in the case you have like a nice action, like a free action, then you can interpret this as the GIT quotient. So I'll put this in a box. And there's a nice way to see this identity using a Cartesian square. So if you look at this moment map going in this direction, and then you take the inclusion of the 0 points in the Lie algebra, both maps are K equivariant. So you can mod by K everywhere. And then you just take the fiber products. That's exactly what the cotangent stack will do. So this is another way to sort of efficiently summarize how to construct this thing. And there's also an important discussion about how to give a Poisson structure on the functions on the cotangent quotient stack. So we can also give it has a Poisson structure induced by the one on the cotangent bundle of straight y. Which I will explain the construction now. So Poisson structure means that there is a Poisson bracket on the functions on T star y. So this is a bracket which satisfies the same axioms that the three are. So this is a standard construction, which I'll recall. So let pi be the projection, and then consider the Euler exact sequence. So we have first vector fields on y, surject onto the pullback of vector fields on the quotient stack. And in fact, this is surjection, and the kernel are those vector fields which are constant along the y, well, curly y. In other words, the Lie algebra of K. So that the sheaf of relative vector fields you can identify with the algebra. And this allows you to interpret the pullback of vector fields as vector fields on here modulo the image here. So this would be y mod y times the algebra. So this is an isomorphism as commutative algebras. One comment here is that this space actually does not have a Poisson bracket. But if you take the K invariance, it does have a Poisson bracket. And that may seem mysterious, but that can be explained by this following construction. So, I'm sorry.
I'm not plenty more with that game.
So the I classical could be sim to y in the algebra. And the tilde classical denotes the Poisson normalizer of this ideal inside sim ty. And sort of by construction, like we have forced the quotient to then inherit the Poisson bracket, and this quotient I denote by P subscript curly y. This is a Poisson algebra. And you can check an exercise that this is precise with the K invariance. The construction. This is exactly sim y, sim T1 times the Lie algebra K. And I think actually I need to make a slight adjustment. If K is a connected algebraic group, this is true, but in general, we need to take the connected components invariance. So if K is not connected, then K is invariance. And then this is the sort of the main construction. And this answers our original question. How do you give a Poisson structure on functions on the cotangent bundle curly Y? It's given by the Poisson structure on sim T1. And one final remark here is that the global sections, so this space is exactly global sections of this. So also here is what's like. So this is the classical setting with Hamiltonian reduction. Now we want to quantize. So by quantize, I mean we construct some associative algebra whose associated gradient is precisely this Py. And the way this is accomplished is by replacing sim Ty by enveloping algebra. Before I do that, I saw Justin wanted me to make this comment. So yeah, this assumption of being good here, we can remove the assumption of being good and then replace this exact sequence with an exact triangle in the direct setting, and everything sort of follows, like the same construction follows, but it just, you have to interpret each step in direct manner. Okay.
So I just make one other. I think you said something about the goodness condition being related to K being finite type or something. But
well, I think it comes for free if like it's an algebraic group.
I don't think that's right. I think it has rather to do with like how far from being free the action is. So for example, if Y is a point and I just take the classifying stack, that's like the prototypical example of a stack that's not good. Okay. Right? It's like so being good, one way to say it is that the subvariety of points where the stabilizer has dimension n has codimension of these 10. You see what I mean? So if the stabilizer is kind of generically big, then it would be good.
Okay, yeah, that's good. Yeah, sorry. Okay, so now we quantize. So this construction has a sort of immediate quantized version. Now just consider this ideal I without the classical superscript to be differential operators on Y times the Lie algebra K, or if you like, this relative tangent sheet, and then let detail the Y denote sort of the normalizer of this ideal in derivative differential operators. So now instead of Poisson bracket, you take the like the Lie bracket of differential operators. And now again, the quotient is going to be an associative algebra. It's an almost commutative algebra, and it's again going to have a description like this. And yeah, so that's the quantized version. Now I would like to discuss sort of a small upgrade of this construction, where you look at Hamiltonian reduction for Harish-Chandra pairs. So this will be like GK. In addition to having algebraic group KX on Y, you also have a Lie algebra GX on Y in such a way that they actually make compatible. Let's explain this construction. Okay, so definition of a Harish-Chandra pair. Okay, where maybe this is the algebra. Okay, it's an algebraic group. It's such that the group acts on the algebra, and there's like two assumptions, and there's also an embedding of the Lie algebras, which is compatible with the group action. Now, suppose you have a smooth scheme Y with the GK action. So this means that there's a so this means that K acts on Y still, and the Lie algebra acts on the vector fields. And this action commutes with the K action. Okay. So we again now have a fiber square. So I'm going to be efficient here and sort of recycle this diagram. So let's take a look now. So you still have the cotangent bundle of Y now maps to the dual of G. And now instead of taking the zero inclusion, you take the inclusion of G mod K dual. Okay, so G maps to G mod K, then you take the linear dual. Again, by this assumption, everything is K equivariant. So we again model by K. And the summary is again, this is a way to construct the cotangent bundle of the quotient stack, curly one. It's again going to be this pushed out diagram of pullback diagram. And yes, still everything here is stack equations. And you can recover the previous diagram by just letting the Lie algebra G equal Lie algebra K. So this is now little k star mod K. This is now 0. And it's the same. So just a slight upgrade before. And the nice setting about Harish-Chandra pair is that the static quotient always maps to the GIT quotient. So GIT quotient means spectrum of the invariance. And you'll see this composite is precisely the local Hitchin map. When we make the appropriate substitutions of Y G and K. So like the framework, it fits very generally. Okay. Of course, we can quantize this again. So this is like Yvonne Moses' favorite thing. Now we quantize. So I'm going to introduce the analogous ideals here, but now with a subscript G and K. So I'll just write it. Wait, so it's going to be sim of G mod K invariance. So this is inequality of Poisson algebras. By the way, this quotient is just sim G mod the left ideal generated by K. And then you can write this again using like this Poisson normalizer mod the ideal. It's going to be P A mod I classical. Okay, and then we take the connected components. Okay, so this is the Poisson algebra. And then the quantized version will be sort of this GK differential operators. So this will be developing out the G mod the left ideal generated by K. And this is not an algebra, but when you take K invariance, it is an algebra. And we can write this again using this general framework. K mod I. Okay. And yeah, maybe I didn't write, but I'll say this IGK is exactly the ideal quotient you have right here. So IGK is sim G times K. And this is the Poisson normalized, just as before. And we have sort of a quantum moment map, or we have the classical moment map and then the quantum moment map. So the action, so the GK action on Y induces maps from sim G to sim vector tables. And then the quantized is I'll denote H classical. It will be from the Poisson algebra. Sorry, this is not, I misspoke. This is not the quantized. This is just the induced map when you mod by the Lie algebra K and then take K variance. Then the quantized version will be developing algebra mapping to differential operators. And now again, if you take the induced map where you kill the differential operators on K, you can do this with quantum map differential operators K mapping to. Sorry, it's a bit small, but these are like the two main instructions. And I can summarize all of this into a nice commutative diagram. And this diagram will be what allows us to state one of like the main goals of the seminar, like showing a local and a global quantization conditions. State this. So there's a diagram. So if you take the associated gradient with the GK differential operators, so this is going to map it to take the differential gradient, the gradient of H. And I can also look at the principal simple map on differential operators. So the curve of a differential operator always maps to the functions on the cotangent bundles. This red case is going to be okay. So I'll denote this by sigma gk, the principal simple map. Then over here, I'll apply sigma y, and this will map onto this Poisson algebra. And this map here is just the classical H. And everything commutes. And so there are now two conditions, a local and a global. So the local quantization condition just states that this local principal simple map is an isomorphism. The global, well, it's not that the global simple map is an isomorphism, but it's that this map H is strictly compatible with filtrations. So I'll write it down and explain. Okay, this says filtration. Okay, so strictly compatible with filtration. So if you have a map A from A to B, where A and B are filtered algebras, it states that the image of the ith filter component of A maps to the ith filter component of B intersect with the image of A. And one consequence is that if both local and global quantization conditions are met, then sigma y is an isomorphism. If local plus global quantization conditions met, then sigma y is an isomorphism. And in our setting of the Hitchin map, the goal will be to show that we can make a global quantized Hitchin map. And this will be done like in the very final talk. So let me give some remarks. So two remarks. First is that we can twist everything by a line bundle. So we can replace the Harish-Chandra pair GK by a central extension of G. So and then the corresponding twist on the differential operator side is line bundle. So NDY with DY L equals line bundle. And there's again going to be sort of a diagram like above. So we cannot actually globalize the we cannot quantize the global Hitchin map, but we will be able to, because then you'll see both sides are just like trivial, like one dimensional. But if you twist the differential operators on BunG, then you can. And then part two is that I assumed here things are finite type, but you can actually upgrade it to affine group schemes. So to affine group schemes. So for instance, K is G of O. All right. So this, I think, concludes part one on the Hamiltonian reduction. Now I want to dive into the Hitchin. This is a good place for a question. Are there any questions? Okay. Yeah.
Can you just say like what K and why will eventually apply this?
Yeah, this will be said in, yeah, I mean, yeah, I'll write it down, but so Y will be BunG with the level structure. So it'll be a bundle plus a trivialization on the disk. K will be G of O. So then when you mod out by G of O, you kill the trivialization. And so curly Y will be BunG. And then, so you have the cotangent bundle of BunG maps to, this will be called like the Hitchin base. I'll explain this. There's, yeah. So these are the like the local differential operators. So this will be like looking at differential operators sort of over the formal disk, and basically like this will be the definition. Like you think of developing algebra G as like differential operators on the group G, which are G.
Yes, another way to like with these kinds of formulas, I was always kind of confused by them because like it's not
Same. Yeah.
totally obvious to me, like why it's not associated algebra or whatever. One way you can say it is if you take the kind of standard universal representation of G common K, so like use trivial representation of G, right, to a representation of the ratio of your pair. This is in what is this method.
Yeah, that's exactly right. So it's like endomorphism of the vacuum module, and then that will be clearly in algebra. And yeah, this is like the exactly this induced module.
Or it's in, oh, the thing in parentheses.
In the yeah,
And then I have a question actually. Yeah, I'm not sure I understand the significance of like the local quantization condition, right? Because it's a condition that's purely on the Harish-Chandra pair, right? So I guess like if K is trivial, this is PBW theorem.
exactly.
And I'm just wondering like what is the significance of it in general? Like how could it possibly fail, for example?
Ooh, that's a great question. I actually don't know. That's exactly what I was. Yeah, so exactly when K is trivial, this is just PBW and there's nothing. I don't unfortunately have an example for when it can fit. Like the only cases I know where you can, it makes sense to check this is with DB localization and with BunG, and in both cases.
Just seems like the kind of thing that would follow formula from DBW, but maybe.
Yeah. I can do my homework and try to answer my question. That's a great question. Okay.
Whereas I guess the global quantization condition, you already gave an example where it fails, which is like we do untwisted differential operators on BunG.
Exactly.
Right.
In that case, like both spaces are like just trivial.
And it's really something global, not BunG.
Yeah.
Yeah. Right.
Okay, so part two. Hitchin map. Construction. So now I assume G is a semi-simple group over C, and X will be a smooth projected curve. Or this will be happy genus at this loop. So we saw us the two parts are this implies that BunG is good. I like
So if you derive everything, you can move the genus right at the two assumptions. I see.
and this is simple solution.
Oh.
Okay, and now C will be this Hitchin base. Is that what it's called? Like
What?
G mod 2. Oh. Yeah, okay. So this, and then we can use
Maybe more canonically G star.
think. That's important. And then we can use the double A restriction theorem and identify with H star mod W. W is a finite group, so maybe I can just take a single slash.
No, that's not right. You're saying it's not the same as the stack quotient. Like 0 has a stabilizer.
Yeah, W definitely doesn't act really on the.
Okay, but I do want to say a single.
But it's not the same thing.
Excuse me. But I do want to say the single. Yeah, like the GIT quotient. This is GIT. So I define this as the spectrum of the G variance on functions of G. Well, this is the same as the spectrum of W variant functions of H.
Just wait. I thought your single slash was the stack quotient, so you're just using a different notation now, or
This will be avoid. I will write it explicitly. Spec sim H. This is the definition. Okay, and in particular, it's an affine space. Notice the dimension and everything. Then you can twist this by the one forms on the curve. So this will be denoted by this product. And now the multiplicative group acts on both spaces because this is affine and this is a line bundle. Let me just take this, just C star the covariant quotient. And
When you say it's affine, I think it's an affine scheme. It's literally affine space. When you say it's affine, you mean it's an affine scheme. You literally mean it's affine space, right? Or
yeah, it's just space.
yeah, because
it's kind of not canonically not about space, right?
Non-canonically, yes. But
So the action is canonical, right? Like, kind of, since you see that action, is it just?
probably just scaling on H.
I thought it was something kind of slightly weirder, but there's like a square or something.
I should actually know this. Well, okay.
there's one more notation. So this Hitchin space will be the global section. And this is a bundle over this. It's false. And this is again an affine space. Identify an affine space of dimension ES minus 1 times the dimension of the group. So this is why you need genus at least 2. It doesn't make sense to say dimensions. And then you consider this space of functions on pitch X. Yeah. Also, we can sort of identify this pitch X very explicitly as a product. So the DIs are the exponents of the operator. So in the case of GLN, the VIs are just like the 2, 3, 4, up to 10. So these are like the color sum polynomials, for instance. So you can construct this, and that actually shows a computation for this dimension. Also, yeah, shameless plug, read the notes there and I circulate things for selection. It's supposed to be spelled out.
And then that's plugging us, plugging against. That's for the GLN case, right?
Okay, so now let's construct a Hitchin map. So there's two ways to construct it. We can do it fiber-wise or you can do it global. I'll do it fiber-wise. It's a bit more clear what's going on, but they're more or less equivalent. So fix E and BunG. And then consider this projection map from E star to spectrum of the G invariance. So I don't know if this slide is C. And then we can twist this map by P. So this induces a map C. And this map is clearly G equivariant, so we can take this small G, and this is exactly what E star P is. This associated G of infinitesimal symmetries of P. And we can further twist by one forms of X to get so we twist by one forms of X, and then we take global sections. So I'll say chalk and just write the result. Everything is happening as so this will be G star tensor with one forms maps to X omega C, and then I can further project to the C star quotient, and this is exactly what Hitch is. And then, if you remember the computation from Ginsburg's lecture again, or if you know already, you can use steric duality to identify this with H1 X. Rule. And that's precisely the tangent space of BunG. Or the cotangent space. So in summary, we have constructed a map from the cotangent primal to the Hitchin space. In fact, this map glues together nicely. We can patch along over all P to now get a map of spaces over X. And in fact, we checked it only on C points, but it is straightforward to check it also works over any smooth test scheme S. In other words, it's a map of stacks over X. And this is called the global Hitchin. Now you can take the induced map on regular functions, and this will be called H classical. And this is the map, so functions on Hitch X I will write by this C classical. Then this maps to functions on the cotangent bundle. Okay, now I can finally state the make theorem for today. Then we can take a break. The image of this map was Poisson commutes. So if this Hitchin map allows us to construct a family of Poisson commuting functions on the cotangent bundle of BunG. And maybe I'll also mention like a conjecture which Grantcharov stated at the very end of his class, which I will not prove, is that in fact, if you look at the induced map on the exterior algebras, then the Skooten bracket on this exterior algebra of functions on cotangent BunG contributes as well. So the Skooten bracket is also true.
That's conjecture.
Yeah.
It's not.
Yeah, I think this is a conjecture of Hitchin, but I'm not sure. Okay, so yeah, maybe we can take a break.
Or actually, you had said 55 minutes and didn't take that long. It's 50.
All right, welcome back. So there was a special request to give a second construction of the Hitchin map. So I'll say it verbally. If you again start with the projection of the layout for G dual to G dual mod G, then you can twist both sides by one forms on the curve. And then you can take like the C star equivariance on both sides. And now this will be a map of bundles over X. And then you can take the stack of sections on both sides. So section means you have a map from X to this bundle, whose composite to X is identity. And then you can see on both sides, you get on the source the cotangent bundle of BunG. This is again using spheric duality, and on the target, you get the Hitchin base, and this is by definition. So this is like a way to construct the global Hitchin map without doing a fiber-wise construction. So no need to check patching over bundles P or being compatible with smooth testing sets. Like it comes for free with this stack of sections.
I think this is kind of a good like forecast how to do the quantization, the whole quantization.
Oh, it's okay.
That's the kind of Carl homology construction.
I had definitely in hindsight, I should have just given that construction.
It's good to see.
It is also written up in our correct. It is written up.
It is written up by yours truly. Okay, so let's give a proof. So the proof of this, I apologize, it'll be a little technical, but let me perhaps give some overview. It'll be you reduce to a local statement. So we replace the global Hitchin map with the local Hitchin map. So this would be like happening over the form of this. You prove that the image of the local Hitchin map is on commutes, and then you lift locally. So let me explain this step. So let's fix a closed point X on the curve. And consider the formal disk. So it's spec of the local ring wants two sets of powers of the max ideal. And you can identify this with the formal power series in the variable tx. Tx is a uniformizer, so it's an element of m squared set minus m. This is called equivalent. And then if you take the spectrum of this is the form of this. And then the embedding of the disk into the curve induces a map on sections from the Hitchin spaces. So we have a map so I remind you, this C is G mod group G. You twist with one force and mod out by the C star covariance. This I define verbally, so you can take C, then you twist by one force on the formal disk. So you can identify this with the formal power series C bracket T dt. And then again, mod the C star covariant. And of course, this space is Hitch X, and this space, I'll just denote Hitch little x, so like the local Hitchin space. And this is a closed embedding, so this induced map on sections is surjective, and then this map is closed embedding, and then the induced map on the sections is surjective. So let Zx the functions on Hitch local x. Then we get a surjective map, which are denoted by theta classical from the functions on the local Hitchin space to functions on the global Hitchin space. And by the way, the reason that this is a close embedding is just saying that any differential form on the curve is, you can uniquely express it using its Taylor expansion around x. So that's what this map is doing, Taylor expander. So this map is searching. And sort of by construction, this fits nicely into a commutative diagram. So we have a commutative diagram. The functions on the local Hitchin space, the functions on the Hitchin space. Then you have the classical Hitchin map. And then you have this local Hitchin. And this diagram commutes. And by the way, I can, just as I wrote down here a non-canonical decomposition of Hitch X, I can do the same for Hitch local X. So
Sorry, what does CL stand for again?
classical.
Oh, classic. Okay.
So without the CL, it means quantized. So I cannot quantize the Hitchin map, not in this law.
There should be a CL on the CL, right?
Thank you.
No X.
No X. Well,
Or is it? It's. Or no, it's good. Yeah.
thank you. I actually made a typo in the notes. Perfect. Yeah, thank you very much. Okay. And this actually gives our proof of the local to global principle. So in this case, it's very trivial. If you can show that the image of the classical Hitchin map, sorry, if you can show the image of the local Hitchin map Poisson commutes, well then by commutivity plus projectivity of this, the image of here also. Like the image here is exactly the image here, but this image Poisson commutes into it. That's the local to global argument. So that's so image classical Hitchin assumptions. And this is done. We will keep doing more and more unraveling, and then at the very last step, it'll just come almost for free by explicit construction. But when you work over the formal disk, you have coordinates everywhere. It's sort of easy to work with. Okay, so let me now reintroduce the Harish-Chandra pair. So we show this. These questions, so let Y is BunG with level structure. I recall the definition. This consists of a pair of a bundle plus a trivialization. Along the formal disk. P triv is trivial bundle on the curve. And then this is going to be a GO torser over BunG just by killing the trivialization. In fact, this is a scheme. It's not a set, it's just a modified scheme. K will be formal this loop space. It's like G of formal power series. The quotient will be BunG. And sort of maybe a bit confusing. So there's no way to avoid this notation. The Lie algebra G in the GK setting will be previously algebra tensor. Like X. So I apologize. There's no avoiding this. I tried to avoid it. So in the GK setting, the algebra G will be GK.
So the reason to see is that there's no automorphism of any G torser that will fix a trivialization right at a point and kills all the automorphisms.
Yeah, that sounds.
That at least shows that it's like 500 sets. And
Yeah. Oh, sure. So you actually is theoretically it's like accurate space.
Yeah, so this is actually cited in James and Drinkel's book, but not true. Okay. Let me now sort of write a large commutative diagram. So I'll start with 6 terms and then upgrade it later to 9. So this is sort of the framework of Hamiltonian reduction tells us that we can look at the moment maps. So the first one, I'm already running out of space. So this moment map is induced by the infinitesimal action of the Lie algebra acting on Y. And then, so this will be like, I'll write it down maybe in purple to the side. This will be straight Y. Then we can take sort of T star curly Y and then take the straight Y points. So this would be BunG product over BunG with the level structure. Then this will be moment map coming to spec sim GK mod GO. And these are closed embeddings. So I just restrict to this space. And here, this. Oh, I will buy you a new quadrilateral variant.
No, no need. I have 50 more where that came from.
Okay, so that is this space. And then we can take the K invariance to get the cotangent bundle of curly Y. This is the curly Y. And this will be another moment now. This is like the algebra P subscript GK introduced at the very end of part 1. So I'll write it down. But now my fingers keep me from the chocolate. Okay, well, then take the K invariance, K is GK. I will omit writing hats and subscript X because it's tiresome. And these maps are both dominant. They have dense image. And I'll write down this is exactly the sim of GK mod GO with GO invariance. This is the P of GK introduced from before. Okay. And all of these maps just come from like differentiating the action. I wanted to draw 3 more terms, but I see if that's not really possible.
Here you're taking out the
Where?
let's say like the price.
So
Second price.
second, right? Yeah. Thank you. Okay. I can actually give you, so like as often the case with Hamiltonian reduction, like with the moment map, you can give the map very explicitly, whereas every case I've encountered you can't. So let me explain what H1CL does. For that, let's compute the cotangent bundle of the level structure. So TP of BunG and X. So this means a bundle plus a trivialization and nilpotent thickening. So it's like spec O mod M to the n plus 1. So we can write this as H0 of X G discover twist by MX with the 1 force. So when n equals 0, you just have the tangent space of BunG is GP star tensor 1 force. This is known. And now when you allow trivialization up to order n, this is like saying you allow poles of order up to n. And now if you take the inverse limit, you allow arbitrary poles, and this is the same as just saying take a section which is right here away from the point. Okay, and now let's describe what H1 does. So H1 classical. So we need to give an element of BunG infinity X is a pair of a bundle plus a trivialization within an F. So F is a function on the puncture curve. And it just maps to I need to give you a functional on GK. This functional, what it does is it takes a so Z will be GK, and it maps to this residue pairing. So you take the residue of the pairing of Z with F. So you pair like the Lie algebra with its dual, then you have just a scalar, then you are left with forms on the disk. Then you take the residue at the point X. And this is explicitly what this moment map is.
So there's something slightly fishy about the upper right. Like, I think it would be. I'm not sure if this actually is affects the correctness of the formula, but GKX star is not an affine scheme, right? Like it's an in scheme,
Right.
So I think you're writing a formula that lands in like GKX star or like putting the G tensor omega on the puncture disk. I'm not sure if it factors through to this.
Well, I think I mean, there's a few notions of dual to take. That is a subtlety here, but the residue pairing allows you to identify K with omega K.
Yeah, exactly.
And that's what I'm doing. Now I just allow the G coefficients.
Right. I'm just saying, if you think about what the recipient of this, like the recipient of this map is, that I agree, it's the space of linear functionals on GKX, right? And I'm saying that's not an affine scheme. So it's just the fact that you wrote the speculative sim of GKX, like I don't think that's, I think if you wrote GKX star, it would be completely fine, but
Absolutely.
just no spec, just GKX star.
And maybe here I should do the same.
No, there it's okay actually, because that, yeah, if you think about like GKX mod GOX is discrete.
Yeah.
So it's really just the usual spec.
Thank you. I will correct that as two things to correct. Great. Yeah. Okay. Now the next step is to replace this second vertical column with another sort of a space, which will be like each horizontal arrow will be an isomorphism due to this residue pair. So instead of taking this functional, I will just take, so then the composite will be, you map this triple to this residue pairing, then you map it to the restriction of F to the puncture list. Let's do that. I tried to fit it there, but I don't think I can.
Lead on to the next board and then lift it up if you're very clever. Set it up. Yeah, you need to orient them.
Okay, so I have X equals star. I'll call it chi1. It maps to like omega K tensor G. So this is what we just discussed. And this is the residue pairing. And then yeah, maybe instead of writing spec sim, I'll write GK module do. So I restrict and I have it lands now in the formal disk, not the puncture disk.
I think there's not supposed to be stars on the right side, right? Because it's
Yeah, you're right. Yeah,
value. Yep.
absolutely. Another typo. Thank you. Maybe I'll need to.
Justin's always got our backs when it comes to whether the star or not, when the star lever.
Yes. And now we take the K invariance where K is G of both. I'll write it specs in this spec sim GK mod G-O, no duals, G-O. And then it's not by 3. Nice. And when you mod out by K, it's exactly going to be the Hitchin, the local Hitchin space. C omega Hitch. Okay. And this is so the first two being isomorphism is pretty easy. So I'll already done. Next slide. I mentioned it a few times, but maybe I'll say explicitly. So it's mapping to the residue pairing. And then chi2 is just the restriction. Just need to check its image times the correct space, and it does. And I just set this up so that again the composite from cotangent bundle BunG to sections on the punctured disk is just the map restriction. You just take F and then you restrict it to the disk. Then chi2 will be you take again a triple, and then you map it to F restricted to just the disk, not the punctured disk. Then chi3 will be that, but then you take like mod K, where K is triple. And then so the only thing which requires some effort is to show chi3 is an isomorphism. Chi3 is isomorphism. So there's two things which we will check. First, that it's a closed embedding, and then that it's has dense image. Okay, so the first step is to identify K mod O with the forms on O using the residue pairing. And yeah, this space again isomorphic too. And this allows us to make an identification in both sides. Here. For it to continue. So back of sim of GK mod of not use the show address for now. This space, you just take the G coefficients, you attach G coefficients, so you can identify the G star tensor omega of x. Be very careful with the duals, but I think it's good so far. And then pitch x of x. Remember, we had this decomposition as a product of forms on the disk with appropriate puts these by these exponents of the layout. And
Sorry, there's no star in the G.
oh,
It's like in the formula. No, right, it's the same.
okay, so this is
That's the left hand side is correct, and right hand side, because that's exactly GK mod Geo star, and then there's the star of G.
Oh, you Justin is star quality.
I mean, if you want, you could just say use the killing form. And
yeah, but that's cheating.
Okay.
Oh man, I have so many typos now. Okay, you have to as a consequence, you have to correct every single one now. May replace okay, and also so basically since I just have a dtx, I'm going to forget the dtx everywhere. So I will say you may replace G with just G tensor O, which is you can think of geometrically as this arc space. The scheme morphisms from this onto is there a dual here? Really? Okay, I've like 6 typos.
You can just propagate it from the top line, probably.
Yeah, you're right. So we may replace this with this arc space, and then I'm just forgetting the DTX. The computation we need to check is independent of this DTX. So replace HX, forget all that with morphism, so like arc space onto C. C is like layout for a G star mod G. Now I think you're actually wait. Okay. Yeah. I mean here there's a G star, which is why I'm a little hesitant to say that there's no G star. Homework for you. Okay. So after we make these replacements, remember what we want to show. This is exactly on the level of functions. So to show it's a close embedding and to show the function map is surjective. So we want to show functions from the arc space have surjectively the G O equivariant functions. We'll omit the dual for now.
You were right from getting their stars. Yes,
Yes.
sorry.
No
sorry.
problem.
Yeah, I'm on the upper right.
Up there
And,
too.
upper right. Yeah, the middle board is fine. Upper right board is stars.
Spotting was kind of fun. Yeah.
Okay, now we're good.
Thank you.
It's confusing because if you have G sub kx, the star doesn't commute with the subscript kx.
The star doesn't need the subscript. Yeah, that's correct.
It does when you have to replace k with a mu.
That's correct.
Right.
No, this is that is like exactly the main difficulty with working on the formal disk, because like every pairing of a space with its dual is done using a residue pairing, and you have to be very careful. Like the pairing on the coefficients has to be like the natural pairing of G with G dual, so you do have to be like extremely careful. That's why I'm trying to not say use the killing. That's just cheating.
It's exactly stereo duality in the punctured disk. When you think about it. In fact, you can prove stereo duality on curve sequence.
Yeah, I know, I read your notes.
Oh, yeah.
Yeah, it was
Sorry,
great.
another pub, like, doesn't readable notes on.
Okay, so to show that this map of, this space of functions is, it's rejected, so there's this nice trick which trivializes it completely, is anytime you want to check the, if you have like a space of functions on some space, you can replace it with a space whose, complement has codimension at least 2. And there's a very natural candidate in our case, namely the regular elements of the Lie algebra. So you replace G with G reg everywhere. So may replace G with reg, since codimension of G reg inside G is 2.
Is that clear? The codimension is like a very basic property.
Well, the G reg is, the codimension is actually 3.
It's the codimension of the complement.
Yeah, G minus, you know.
Yeah, the codimension is actually 3.
What about?
And this does not, since this does not affect the full sections.
Probably some normality condition, if there's some kind of. Be normal somewhere for that to be. You're using a hard talk lemma, right?
Yeah, but it's not on space.
Yeah,
Oh my god,
everything is
very,
out.
very, very. Yeah, sorry.
Yeah, and
Yeah, wait, kids.
sorry,
We're taking kids, like, honestly.
Yeah.
That's.
yeah.
Sorry, how's it being used? So. Cat space is running.
So I am saying if you replace this space with G reg mod G, well, okay, but yeah, with this space, if you replace G star with G star reg, then the arcs are this.
Yeah. It's not that the arc space number, but there'll be. The functions on the arcs will be isomorphic.
Functions on the arc function.
Yeah, I see. I mean, I guess, yeah, so the point is the arcs map to G star by evaluation of the center. By evaluation of X, right? And so even though the arcs are in the dimension, it's like they project to G star and it has a codimension of these 2, and so I think you can prove. Yeah, it's my function. That's functions that makes sense. And yeah.
Okay,
Okay, now I will not define G reg, but I will say that the key property is that the projection map is now smooth. And the group action on the fibers is transitive. That's enough to finish. So now the projection is smooth. And G times transitive on the fibers. And that this shows surjectivity. of
But this ought to be something that one learns standard geometric relativity. It's not reg semi-simple, you're including the regular nil
Yeah.
nodes to make this codimension.
no semi-simple is way too.
Yeah, okay, yeah, because that would just be the vanishing of the.
Yeah,
of
that,
the,
no,
the discriminant of the characteristic polynomial.
yes.
But okay, so that is definitely, or not, it's not often. It is.
So like for SL2, this is everything except zero.
Oh, beautiful, okay, yeah,
And then
Yeah.
and then that's.
Yeah, I wanted to avoid the definition and just state this property.
And so it still is smooth even when you include those regular. Yeah,
let's
okay,
do the constant.
goes on, yeah,
Yeah,
okay.
I think you can read Ginsburg's book
Oh, and no, Professor No.
on chapter
Also
6.
said this stuff too.
Yeah.
No, this is very-
Yeah, and this kills it. I mean, maybe this isn't like a legit proof, but the way I think of it is. Okay, well, this is not a trivial, like Greg does not split as Greg mod G times G, but it like behaves as if it did. And then when you look at what that states over here, you have this arcs into G, split into arcs into G reg cross C, and then the arcs into the group G, that's just GO, and then you have like a function from GO, which is G covariant, so that just dies. And then you literally have this as a mass. That's one way to see it. Also, this trick is this trick also proves smooth. That is dominant. So also, show is dominant. We use a what's the phrase, like a formal, like a smooth lifting criteria.
It's almost smoothness.
Formal smoothness. Yeah, so essentially this where's type 3? Yeah, so if you replace G by Greg, then you can actually see that the image land of kite 3 lands in Greg mod quantum G. And that, I mean, that is dense inside without the regular.
You mean the image contains.
The image contains that, and that is dense inside, yeah. And the reason why the image contains that is because of like lifting arc spaces. Like you have a arc on this quotient, and you have a smooth map, then you can lift it here, but just by going piecewise. Like you lift order 2, then order 3.
Actually, maybe we can even simplify this further because that map has a section, right?
The constant section.
The other constant section. So I guess that.
Of course, that's
yeah,
even easier.
That is
Somewhat non-trivial, but.
Yeah, I liked your proof in office hours more.
okay.
Yeah,
Wait,
so
cost
yeah,
factor.
I forgot. So the other references.
But maybe it's kind of circular because this maybe also uses.
Oh, I
Yes.
see, this is probably, yeah, probably some semi-unpacking
Yeah.
Poisson's theorem process,
Yeah.
okay.
So now we're basically done. So we proved the lemma. And now we are basically there as a corollary, right, in the P board. The local Hitchin map Poisson please. So remember we have this Poisson algebra of functions on the local Hitchin base. And we have this local Hitchin map mapping to functions on the cotangent bundle. And the way I've said I just erased. The diagram is up is so that this map actually factors through this H3 and phi. This diagram commutes. Essentially, both arrows, I said before, I'll say again, it's the map where you take a function on the Hitchin base and you restrict it to the disk, and then you take mod k, like the induced map on the GIT function. That's what both of these arrows are doing. So this diagram commutes. We showed chi3 is an isomorphism. So we need to show H3 plus 1. Because by the way, all these maps are of plus 1 algebras, they respect the plus 1 bracket. So we need to show H3 has image plus 1 computing. To do that, we explore this space. So remember this space with thin GK mod GO with the GO invariance. This is where you reduce something extremely explicit, which I'll just cite and not write. So you can consider the completed symmetric algebra. That into PGK, which I'll remind you what it looks like. Okay. There's a completed symmetric algebra. And you can show by just directly writing a formula, this map is surjective. Reference Bailenson-Drenfeld book 2.4.2. And now we're done because you see the source is precisely the Poisson center of the completed symmetric algebra of GK. So of course its image will be trivial. So then the image is the whole thing. So the image has trivial Poisson bracket. And now we're done because if PGK already has trivial Poisson bracket, which respects the Poisson structure, then that it has image with Poisson. So source center completed GK implies GK Poisson has trivial Poisson bracket. But it already has trivial Poisson. And now that completes everything actually. So we proved the main theorem, and in the final 10 minutes, I want to sort of give a glimpse to the future. But again, here's a good place for ready for questions. Comments. Final. Okay, suppose we have found a quantization of the global Hitchin map. Then I can show that the Hecke eigensheaf is non-zero. So let's just set up the notation. So assume have parameter, the quantization of the global I'll write what this means as a theorem. Prove in quantitative.
It's probably more like top 29 or something like that. But if you're counting from the very beginning, we're talking in this order.
So it's 9 plus 9 plus 8.
Every time I upload to YouTube, I have to learn the control.
So there exists a filter commutative algebra. Hey, ZX without the classical, whose associated gradient is the classical. And such that this commutative diagram I drew in the beginning with the open global quantization condition is met. So it exists. I mean, such that the diagram the x maps to grr of constant differential operators BunG. I'll just write it, Frank.
Retake the curve, I guess you also have to posit the existence of this map, right? So you have filtered commutative algebra C together with.
Yeah, I guess I tried to encode that in the existence of this commutative diagram, but yeah.
But it exists in the filter. Right, and you're taking associated.
Yeah, there's just a strictly compatible with filtrations. Hitchin map, yeah.
We go constructing the maps part. Right?
Yeah, there's a maps. Yeah, so the global quantization set up this, or the local plus global set up this, for example. And furthermore, we have curve of the TDO on BunG is equal to just functions on the cotangent bundle. This is the classical. there exists H map. Yeah, that might be great. And I'll put it likewise. One of these. Okay. Assuming this, let's carry on. So let this over LGX, and there's like many equivalent ways to define it. Using like Hecke and Frankel, but for us, we can just say take the spectrum of this commutative algebra. I've not told you what this looks like, but just take the spectrum and then take an over signal. And then consider the associated D module in BunG. This is a very standard way to construct it. So you just take the prime mod the left ideal gen by signal. Or in other words, the signal prime is a D module on BunG. The prime module on BunG. Okay. Theorem. This is also, by the way, called the Hecke associated to the oper. Theorem is singular support is the global nilpotent cone. This means it's the zero fiber of the classical Hitchin. Before I denoted the Hitchin map by H, that was like the induced map on the regular functions. But here's the map of space stacks. Okay, so let's prove this. Sorry. So remember, singular support is like the, the definition we can use is just, it's saying that the associated gradient of this space has, so this is like a space over the open bundle, it has support equal to this. It's like equality over T star function. Okay, so we use a factor mu that is proved, for instance, in Ginsberg's paper on the global nilpotent cone, that mu is flat and its fibers are all dimension equal to BunG. Okay.
Goodness.
Oh, sorry.
Yeah, and so like this sentence together with this theorem immediately implies that the Hecke eigensheaf is a holonomic D-module. This just means that the dimension of a singular support is equal to the dimension of the ground space, which is BunG. So I guess find this holonomic.
It also implies that it's like, if we didn't know that this map was flat, then it's possible that the C prime sigma would have, there'd be some pores and it could be in multiple homological degrees, but because it's flat, this tensor product operation is exact, and so you actually get a D module system.
Cool, I did not know that. Yeah, thank you. Yeah.
So it's a perverse sheaf, basically. Not obvious.
Great. And okay. So being flat, one way to retrace it is by saying that third D prime is flat over third X. So this is Hitchin in flat. And if the curves are flat, then without the curves it's flat. Flat over X. And now the prime is flat over Cx. So this means that we can compute the associated gradient of D sigma prime. It's like associated gradient then becomes an exact commutative. This is like the key non-trivial step. Follows this there. Gradient D sigma prime. Use. Well, you write it as gradient prime mod gradient D prime times the ideal. And of course, Gertie times functions on D star energy. And then we just model by the ideal term by sigma. And I have to use one more word. So the singular support is defined as the support of the sky, and of course the support of the sky vanishes from this, which is just the 0.5 obligation. Singular support prime. It's a good place.
Any questions? Comments? Display stars?
So you're claiming that this is a Hecke eigensheaf. What's its eigenvalue?
Yeah.
Yes, with the eigen.
What was the eigenvalue? This was in your topic. Yeah.
Well, you didn't define this C, but it's going to be something that lives overlooks this. So like an oper is a G-checkable system with some additional structures. So like the eigenvalue is the G-checkable system that underlies the oper. It's not on the board, but
Oh, yeah.
so it's part of Hecke and Frank. It's like there's opers are local systems with some additional structure, but on the other hand, they're identified with this center or whatever, and it's here. So this Z is functions on global opers.
Oh, gotcha. Thank you.
That's all I did.
Yeah. And it's not, I mean, something else that needs to be proved as part of this theorem is that this global quantization is compatible with Hecke in an appropriate sense, and so you actually get a Hecke eigensheaf. That's something else that has to be proved in Hecke. So sorry, just to be clear, the flatness was like, I guess it's technically used in sort of like line 4 because it's what I was saying is like, since mu is flat, therefore D prime is flat over Z, and so when I tensor up the case sigma, I get something that's perverse. Yeah, okay.
Yeah. I'll add that to the notes.
kind of interesting because I think there's another way of approaching like this fact that it's reversed and the fact that it's non-zero that
I have to explain that with the Whittaker stuff.
I mean, I can't explain it easily, but there's a recent paper by Sam Raskin and Young version of different things along the line. Yeah.
But your things like that.
Well, okay, so I don't know about the perversity, but for the non-zero part, it's like you can compute the kind of first Whittaker coefficient of these guys and show that it's non-zero. So there's this, and if you look in the Jerusalem 2014 notes, there's this thing you plus up the diagram, and what that does is exactly like computes the kind of Whittaker coefficient of these localized D modules. And so in particular, you can make non-zero, you can prove that these Hecke eigensheafs are non-zero.
That's really cool. Yeah, I don't know what the coefficient is. Oh, I'll take a look.
It means you like pull back to G, and then you sort of do this. It's like Whittaker averaging against Whittaker. Yeah.
And a question. So is the local system right? It's just a local system.
It's a local system with some additional structure. It turns out that the global opers embed into the local systems.
So I mean, a local system is supposed to support you is supposed to support it's more or less right?
I think there's we need to find it's like it's much more complicated, right? There's a condition on the over, it's only half dimensions, but
This is a different kind of singular support. Right, we're talking about a D module on BunG. We're saying as a D module on BunG, it has a certain singular support. Not talking about local systems, G-check bundle with flat connection X, right?
over is like half the dimension of all G-check systems.
Yeah.
Branching is it, yeah.
I mean, there's Langland's duality here, right? It's a statement about the system.
Any other questions?
Let's think this.
It's the same. The Hecke eigensheafs, they're not these